Thank you, Sergi, for your presentation. And let's start the first session for this Photonic Integration Week. Let's proceed with. Now is Pascual Muñoz, who is going to talk about the photonic technology platforms.
Okay, thank you, Ruben. Okay. So, okay, there it is. So, thank you, Ruben, for the introduction. My talk today is titled "The Future of Silicon Nitride Photonic Integration Technologies," and well, it is divided in these three parts, like the starter, and then the main course, and the dessert. So, for introduction, I'm going to say what is photonics and what is photonic integration. So that means that maybe half of the room is going to get an app for those few slides. But I think it's important because not everyone in the room is very, very deep into photonics. And then I will make a very brief summary on the available photonic integration technologies. Then as main course, I will talk about one of the technologies, which is silicon nitride photonics, which I believe is particularly relevant and is getting a lot of attention in the very recent years. And I will show, and I have selected three applications which I believe that are very representative and that have been very representative in the past years at different wavelength ranges: visible range, biophotonic sensors, near-infrared, antenna beamformers, and from the visible to long near-infrared frequency comms. Then as the last part of my talk, I'm going to talk about the future developments of the silicon nitride photonics platform, in which me, together with our spin-off company, VLC Photonics, and the National Center for Microelectronics, and we are involved. So, as introduction, well, photonics, I think that, as I said, most of us know what photonics is, but it's the branch of physics that actually deals with the properties of photons. Okay, those small particle wave things that are the constituents of light. And what for me is important is not only the different things that one can do with photons, which are right in here, like generation, emission, and many others, but to me it's important to highlight that photonics is something that happens over the whole spectrum. Now we are sitting here, and unless that you are taking an app already, you can see me because of photons, and that is a visible light. Okay, but there are many, many other things that you cannot see. For instance, when you just take an optical fiber, which is used for long distance transmission, there is light inside, but that is not visible light. That is infrared light. Okay, and many, many other wavelength ranges that I will show later on, and that are relevant for many applications. So that is photonics. And then, what is photonic integration? So, in many, many application fields where photonics is used, the systems that make a given functionality are somehow built out of discrete components. That means, for instance, I have a laser here with me right now, the red laser, and then I have, I don't know, a combiner. So these are two different components, and I somehow splice them together and make a slightly more complex system. You have a picture of such a system here on the left-hand side. So that is a box, I would say, the size of this table here. And therein, there are several photonic components with fibers. You splice them together, you put some electronic control, etc. And you make this, let's say, box with a given functionality. Photonic integration allows you to turn this into this on the right-hand side. This is a photonic chip. You can more or less guess the size of a typical photonic chip because it's laying on the tip of the finger. But of course, you don't use it that way. You just put it into small package And if you compare the size of this to this, well, I said this is the size of a table, and you can guess as well how small is this compared to this. Of course, to turn your application idea into a product-like thing, you need to go through different steps of the supply chain. So the actors that help you to turn your photonic system into a photonic integrated system. And of course, they are composed about software vendors that help you to somehow simulate and design the behavior of your photonic system when you put it into a chip, and that somehow can make a blueprint, or what we call a layout of your chip, so you can send it to manufacturer using wafer scale manufacturing techniques. And after manufacturing, for instance, you can singulate your chip and then you put it into a package. Of course, you can test it as well to end up with a product. Okay? So that is, in very short, what photonic integration is. And linking to a previous slide on photonics in general, I'm showing here the photonics spectrum. So you can see here from, let's say, visible to the far infrared, this is wavelength. And I allow myself to, let's say, not very strictly speaking, to divide the wavelength ranges in the, let's say, the main applications that are used in those wavelength ranges. For instance, in my case, I come from the telecom world, so we actually been working mainly on the near infrared up to a few years ago. Basically, if you are somehow familiar with optical fiber transmission, you will know that, let's say, the most convenient wavelength to operate an optical fiber, because it has low loss, it is 1550 nanometers. That is exactly in the middle, or more or less in the middle of the near infrared. But there are other applications also for tele and datacom that can benefit by using other wavelength ranges in the near infrared. Then there are applications like biophotonics, and you're going to hear at least a couple of talks about this along the Photonic Integration Week, in which the main wavelengths used are in the visible range. That is the visible light that I mentioned at the beginning of my talk. And if you go to the other side of the spectrum, in the mid-infrared and also close to the far infrared, there are a lot of applications for sensing, and I will be a little bit more specific in the last part of my talk. So what do we have? That is photonics, let's say, at large. But if we want to make a link with the technologies available for photonic integration, then you can have a look at the bottom part of the slide, where I just draw these rectangles, which actually give you an idea, rough idea, of which materials you can use for photonic integration in the different wavelength ranges. So 3-5 semiconductors are the ones that have nice properties in the near infrared for photonic integration. Silicon nitride on top of silicon oxide is used from the visible to, let's say, the upper part of the near infrared. And then there is silicon on top of silicon oxide, which has a slightly comparable, slightly reduced wavelength range for application. So I won't go into much detail, but if I have to summarize the benefits or the properties of each of the material systems, because what I can say is none of them is, let's say, a winning candidate for all the applications. If I have to say something positive about 3-5 semiconductors, I need to say that it can have active and passive components on a chip. And when I say active and passive components, when I'm talking about photonic integration, I'm saying passive components like the waveguides. And when I say actives, I'm talking about the optical source, like, for instance, a laser. I'm talking about amplifiers, but also I'm talking about modulators and detectors. So the benefit of 3-5 semiconductors is that you can have everything on a single chip. All the components, more or less, all the components, I will put an asterisk here, but all the components that you can imagine in a photonic system, you can have on indium phosphide. Then I can jump ahead to the silicon on insulator, which is silicon with silicon dioxide, and because it has everything except the laser. So all the actives, like, let's say, the modulators and the detectors, are as well present in that technology. And let's say the benefit of this technology is its footprint. It is by far the technology in which you can get the smallest footprint devices, and footprint matters because that is wafer space and that is money. And another important thing is that it is actually manufactured in the same lines where you manufacture the CMOS electronics, for instance, that is used, for instance, to do the computers and your cell phones. Then in the middle we have silicon nitride, which is passive, meaning that you cannot generate or detect light. You can only guide light, but it is very low loss, and that gives room to a lot of applications, and it is as well CMOS compatible. Apart from that, it runs from the visible to the near infrared, so it covers a very broad part of the spectrum, and that means covering a lot of application domains. So these are the advantages of silicon nitride. So that was as introduction. Then I want to talk a little bit about which applications you have in silicon nitride. In silicon nitride, for instance, you have applications in the visible range. So I just copied again my, let's say, spectrum here. There is some part missing, I don't know why there, but okay. A visible range here for biophotonics, and then I'm going to present one of the applications which is very relevant in the field. And by the way, these slides are courtesy of Professor Laura Lechuga from the Institute of Nanosciences and Nanotechnologies in Barcelona. So usually, for instance, in an analytical laboratory, you have a lot of instrumentation that makes use of photonics. But those are somehow bulk equipment, because it makes this equipment is built, as I said before, by combining discrete components. Okay, and that means that that because of size and because of, let's say, the very specialized working of this equipment, this is going to be limited to centralized labs. You're gonna need to have specifically trained personnel and for these equipments, and that way of building the equipment is somehow expensive, because, as I said, you need to source different components, put them together from different vendors, stabilize the whole system, and then make it run. That means that this kind of equipment is not available for everyone. So if you imagine, let's say, where can I find these sort of equipments? It is likely that you find it in a hospital, but it is maybe unlikely that you find it in your local care center, because it's, let's say, costly, bulky, and requires very highly trained personnel. So that means that somehow the technology is constraining the use or the application or the spreading of these analytical techniques. You can turn that into a benchtop instrument as well, and then you can bring it a little bit more closer to people. But ideally, you would like to have a point-of-care device. That means something that you can do out of a laboratory, so you don't need a laboratory environment to run it. Then you can make it somehow fast and with many other advantages related to sensors that I will maybe detail in a few minutes' time. And another important thing is that somehow, if it is used as a first screening device, it should be somehow user-friendly and work unattended, more or less like, for instance, the devices that are commonly used nowadays for glucose monitoring. So ideally, one would like to take like a small part of a sample, not a big, let's say, a small amount of sample, and just run it through the device, get the results in, let's say, any platform, any digital platform, and somehow be used as a first screening test. So photonic integration can help to go from this to this, because it can turn equipments that are, let's say, using, let's say, photonics or a photonic chip inside a laboratory equipment, to turn it directly into a lab-on-a-chip device. So actually, you see these two pictures here. As I said, this is a laboratory environment, and this is a wafer with devices that are used for photonic sensing. There are many ways of doing photonic integrated circuits for sensing, and I'm just going to give an insight on one of them, which is of the proposed by the group of Professor Lechuga, and it is based on, let's say, a relatively very simple device. And that very simple device is a waveguide device. For those of you that are unfamiliar with photonic integration, a waveguide device is something that takes the light from, let's say, a given point, and it drives it to the other side. Okay, so sort of, let's say, light conduit that goes into a chip. And this is very simple, and it can be fabricated in mass using wafer scale techniques. And the device that I'm going to talk about is actually composed of two different types of waveguides. One waveguide which is small, and then another waveguide which is slightly bigger. If you want to think about this, and I see my students sitting on the back, I think I made this analogy in class, and I bring it here today as well. You can think about these conduits as, for instance, the roads and the highways. So, for instance, this tiny one would be a road where maybe only one car fits, okay? And this might be like a slightly larger road, like an avenue, like the Avenue of Naranjos that we have here, where they may fit a few more cars, okay? And if you use these two different roads to guide light, then you can have a very nice effects, and I think the video is going to run. I'm going to try to explain it live. So here you have your photonic chip with the waveguide, and this area is somehow activated so it can capture actually what you want to sense with the photonic device. So there is some chemistry that activates this area, so actually it collects the target substance or analyte. So you shine light onto it, and the light goes through the first light conduit, through the first waveguide, and it travels on what is called the fundamental mode or the propagation mode of that waveguide. For those of you that are familiar with electromagnetics, I think that is clear. And the second part of the waveguide supports more than one mode, supports two modes. So part of the light is split into, or is kept into the fundamental mode, and part of the light is somehow fed to the second order mode. And what you get at the end of the device is interference. So actually these are two electromagnetic fields that are interfering one with each other. But the beauty of this, in my opinion, is that the field that is on the upper side of the waveguide feels the analyte, so it interacts with the biologic substance, whatever it is. So the interference that you get at the outside is somehow altered because of the presence or not and the amount of the analyte that you are trying to sense. So as I said, this is a very simple device. It's just a straight waveguide, and it allows you to sense many things. If you are interested in the applications, well, it has a lot of applications. Key here is, for instance, maybe photonics is the underlying, but the key here is how you apply chemistry to, let's say, this part of the device in such a way that specifically what you want to sense gets attached to your device and nothing else does. So that is one of the applications, as I said, and this is silicon nitride, which is a material that has been in microelectronics for long, and it is very well known, and it has a very good manufacturing properties, and that is why it's advantageous in this case, because it's a very simple material to manufacture and process, or relatively simple compared to many others that I've shown before. The next application is in the near infrared, so I just move my arrow from the visible to the near infrared, and it is more related to the telecom world in this case. So in today's world, I think that we are all aware that we're using many wireless devices, like our cell phones, for instance. And there is a growing need of increasing the capacity of these RF devices. We're going to get a talk by Professor Kamani tomorrow, and he's going to give more details on this. But I wanted to bring this example because I think it's very relevant as well. So when you need to increase capacity, basically you need to increase the number of, let's say, areas in which you divide your wireless coverage. And you can also do so, let's say, using antennas that have a uniform radiation pattern, but you can do as well by making use of antennas that have directional beams. Okay, so for instance, imagine that you have several antennas here, and then I see my student Juan here is sitting in the backside, so he's not paying attention to me, and he's just having a look at let's say, HD video on the YouTube, and he needs a lot of capacity. So there is a system that somehow points a beam to him. If the system was run by me, would kill him because he's not paying attention, but it's like, you know, being governed by someone just willing to deliver more capacity. So it's pointing a beam to his cell phone and is pointing all the capacity or a lot or more capacity to his cell phone. That is one of the possible application scenarios. There is another one in which, for instance, these antennas can be mounted on a plane. Okay, and this is the one proposed by a group in the Netherlands, in the University of Twente, and the spin-off companies Lyonics, Atrax, Lyonics International. And in this case, it is pretty evident that you cannot have a mechanical system on top of your plane trying to steer the antenna to a satellite because of many reasons, right? Main of them is there is a lot of drag because of the plane moving, and it would be a very, very complex mechanical system, apart that would take a lot of fuel from the extra fuel because of the drag. So patch antennas are a solution that are of course used as well in civil applications, in land civil applications. These antennas are composed of many elements. If you are familiar with beam steering, you will know that to steer a beam you need elements, and that you need to control the relative phase between the elements. And that can be done with electronics as well, but it has mainly two drawbacks, or three drawbacks, I would say. First of all, it's bulky. These are like very big systems with, let's say, microwave cables, even pipes, depending on the frequency. As far as you grow in frequency, you need bigger microwave transmission lines. And then, second of all, it is somehow limited in bandwidth. So microwave components operate in a limited bandwidth compared to other technologies. And the third of all, I said bulky, I said it is narrow band, and then the third of all, it needs to be tunable. It needs to be tunable. For instance, in this plane, that you want to point to a satellite in a given frequency band, and then you need to move like 2, 3, 4 gigahertz to another band for another satellite. Then you need to make it tunable. And those 2, 3 gigahertz with in a 15 gigahertz range, that is broadband, and that is something that you can hardly do with electronics. So the group and the companies in the Netherlands, in Enschede, they propose a photonic chip, and you can see the layout here, which actually have 16 elements to tune an antenna of 16 elements. And it is a small chip. It is just 1 centimeter times 2.4 centimeter. And they actually manufacture it. You can see it here. You can see it here, and compared to the size of a 20-cent euro coin. And you may wonder why it's important to use, for instance, in this case, a silicon nitride technology. Well, in this case, you're going to put some sort of delays inside the chips. And those delays means that the light needs to spend, let's say, some time inside the chip. Of course, all the technologies have loss. That means that the more time the longer the waveguides are inside the chip, the more loss you get. And for that, it's crucial to have a technology which is very low loss, and that is silicon nitride. Okay. In fact, the technology that is specific for Lyonic has a very, very, very low, I would say, world record loss of even less than 0.1 dB centimeter. Again, and this is CMOS compatible fabrication process. So this was another one of the applications. And then the last of the applications I wanted to talk briefly is, let's say, another one which is a little bit more fancy, I would say, more sophisticated and more exotic. And this is optical frequency comms. So in this, oh, sorry, I just skipped this one. Yes. Okay. So optical frequency comms. Optical frequency comms, and in this case, for these technologies, they are covering all the near infrared. And this is done in silicon nitride because it has the right properties to do these things. This is a nonlinear photonics application. That means you shine some beam of light at a given wavelength into your photonic chip, and then as an output you get all these wavelengths, okay? All these wavelengths which are very precisely spaced. They are coherent to each other, so actually if you beat them with each other, you get very narrow RF tones. And this has many, many applications depending on the wavelength range, either RF and coherent communications, metrology, biomedical imaging. So the application set is very, very large. And it is all on top of a silicon nitride chip, because as I said, it is advantageous in terms of loss for high power applications, which is what you need to actually start this nonlinear process. Okay, so that takes me to the end of the second part of the talk. But then there is something that I have not said. What about the other range? Okay, what about the mid-infrared? There are, let's say, other technologies that can be used in the mid-infrared, for instance, germanium on silicon. But what about silicon nitride? Why not silicon nitride? Because if you take a close look to the transparency range of silicon nitride, so that means the wavelength range in which it can guide light without significant absorption, then it runs from the visible to, let's say, close to 7 microns, I would say half of the mid-infrared or more. And why it is not used in the mid-infrared? It is because it is usually combined with silicon dioxide, which starts absorbing at 4 microns. So the next part of the talk is making a vote, positive vote, for bringing silicon nitride photonics into the mid-infrared. And if you wonder which applications you have in the mid-infrared, well, this is an excerpt of the applications identified by the MIRFAB manufacturing pilot line. David will tell a little bit about the pilot lines later on. And it has many, many civil and non-civil applications, like, for instance, gas trace detection, gas distribution, safety and security, and many, many other. So those let's say, the analysis of those things is those molecules of many gases, for instance, have vibrations in the mid-infrared, vibrations that are unique. So actually, if you get a vibration at a given wavelength in the mid-infrared, you can tell with a lot of certainty that it is this gas and not that other. Okay, so this is the platform that VLC Photonics and CNM developed in the past year, and we have support from the university. And it actually has silicon nitride surrounded by silicon dioxide. So it supports a visible range from wavelength range from the visible to the long near infrared, and it has many features. So maybe we can talk about them later on if you wish. But the thing is that it's also running in a wafer scale technology, and it has been running for some years in different manufacturing runs. This is going to be maybe part of the course that VLC Photonics is going to give in the coming years, but this is an opportunity to get your photonic chip or your photonic idea manufactured into a chip. So today, silicon nitride photonics has a guiding which, as I said, is restricted, and I have also identified many other limitations, that, for instance, resolution in manufacturing, the type of tuners that are used, for instance, in the Lionic chips are thermal tuners which consume a lot of power. And one of the, let's say, worst things of silicon nitride, it's passive, and that means it cannot detect, modulate, or generate light. So I believe that there are ways to solve this, so actually to turn this VLC CNM silicon nitride photonics platform into a fully working platform on a chip by heterogeneously or hybridly combining with other technologies. For instance, how to extend the guiding range. As I said, the material here to blame for the limited wavelength range of transmission is silicon oxide. So the naive, let's say, approach is actually to get rid of the silicon oxide. And that means, for instance, creating a membrane waveguide. And that is actually that we are currently doing. There is another objective in our platform, which is to allow users of this silicon nitride platform to make either coarse resolution devices, but also very fine resolution devices. And we are aiming to develop and combine two manufacturing techniques that allow you to have different resolutions at different areas of your chip. Then next is to put into the silicon nitride some active device, which is the modulator or the tuner, but which is fundamentally different to the thermal tuning mechanism that takes a lot of power and is somehow slow, and that can be used for a very broad range of wavelengths. And we believe that is going to be a micro electromechanical modulator. And finally, we recognize the need of having some actives. When I say actives now, I refer to the sources and detectors combined with the passive silicon nitride chips. And there are techniques like, for instance, transfer printing, in which you can manufacture your actives in a technology in a given wafer, and then you can somehow just take them and stamp them on top of your passive technology. And that is something that we would like also to explore. That is a work that we're going to do with a cooperation in 3 parts from not only us at university, but also CNM and BLC. And hopefully you have it available in the next year as a full photonic integration platform. So as a conclusion, I like to show this slide again, so referring to the application range and the wavelength ranges, and particular to our platform that is of use now in the visible and near infrared, but our goal is to extend it as well to the mid-infrared and to incorporate actives. I don't want to conclude without just making a little bit of advertisement of the European Conference on Integrated Optics, 20th edition. Is going to happen at the end of May here in Valencia, exactly in the same auditorium, and also in the area below with exhibit and parallel sessions. And there's going to be a nice combination of academic and industry research exhibits as well, and also many other events. So hopefully you can attend as well. So that's all from my side. Thank you very much.
Thank you. Thank you, Pascual, for your presentation. Any question from the audience? Okay.
Ah, ya está. Déjales un poco de tiempo, ¿no?
Thank you, Pascual, for your nice presentation. I just was wondering, do you know if Professor Laura Lechuga is working with SPR still, in combination with the device you just mentioned?
As far as I know, they made a very, very good SPR devices, surface plasmon resonance devices, and that was part of past research. And I think that they also made a product. They spin off a company and they sold the company. I'm quite sure that, well, I'm quite sure because I visited the lab, so they still have the SPR devices in the lab. But they are putting as well a lot of effort in the photonics device, in the silicon nitride photonics device. But still they work on that, yes. Any other question?
Okay, no. If not, let's move to the next speaker. Thank you, Pascual, for your
Thank you.
questions.